Alright, in this next video in section 13.4, we're going to look at how to compute some partial derivatives. So in the last video, we just defined the partial derivatives in terms of difference quotients. And I have the definitions here, okay? And what I want to emphasize right now is that looking at, say, the x derivative, right, it's only the x variable that is changing, right? We're wiggling x from x up to x plus delta x, but y there is held constant, okay? And then likewise for the y derivative, we're just changing y, right? Y varies from y up to y plus delta y. X there, though, is held constant, okay? So a takeaway from this is that in order to compute partial f partial x, it's, instead of just going straight from this limit definition, we instead could just treat y as a constant and then take the ordinary Calc 1 derivative of our function with respect to x. Of course, the benefit here is that we get to avoid the difference quotient computation, which you likely recall from Calc 1 is kind of a pain. And also, all the derivative techniques we learned back in Calc 1 are just going to carry through and help us out in making these partial derivative calculations, okay? Now for the y derivative, same idea. We're going to just treat x as a constant and then take the ordinary Calc 1 derivative of our function with respect to y, okay? So let's go ahead now and see this in action. So looking at problem number 1 on the worksheet, it says to find the first order partial derivatives. So in the next couple of videos we'll look at second derivatives, but these are just first derivatives. And so let's say for part A, I want to find the x derivative. Okay. Well, what I said in the last slide there is that, well, I'm just going to treat y as a constant and just differentiate in the usual way with respect to x. So the derivative of 2x squared, that's just going to be 4x using the ordinary power rule. Differentiating 3xy, well, y is now held constant, right? This is treated as a constant, and I have a minus 3, which is constant. And the derivative of x is just a 1, right, with respect to x. So I'm going to just get, in that case, minus 3y. Now the derivative of 5y cubed, that would just be 0, right, because 5y cubed is being held constant there, so the derivative of a constant is 0. So in fact, this is my answer. Okay, not too bad. Certainly a lot easier than using the limit definition. Okay, now for the y derivative, really similar kind of thing. The derivative of 2x squared with respect to y would be 0. Okay, so then moving on here, now the 3 and the x are constant when it comes to differentiating with respect to y, and the derivative of y is just a 1. So this is just going to give me a minus 3x. And then differentiating the 5y cubed, I'm going to get a 15y squared. All right, and that would be the y derivative. Not too bad. All right, let's press on then to part B. We have g of xy is e to the x plus 2y times the sine of x plus 3y. So if I'm going to say compute the x derivative, okay, notice I have an x in the exponential term as well as in the sine term, so I'm going to need to use the product rule for this because I have the product of two functions that depend on x. And so I'll go ahead and differentiate first the exponential term, and that's going to give me an e to the x plus 2y. That doesn't quite look like a y there. Here we go. And then I need to apply the chain rule here, and the derivative of x plus 2y with respect to x is just going to give me a 1 from the x. The derivative of 2y there would be a 0. And so I'm just going to put a 1 right here for emphasis, okay? And then that derivative will multiply with the second term, which is sine of x plus 3y. Okay, then we're going to add to that the first term, which is the exponential, and then I'm going to multiply by the derivative of the second term, the derivative of the sine. So that's going to give me a cosine of x plus 3y. And then again, I need to apply the chain rule here. Differentiate the inside with respect to x, and the derivative there would just be a 1 here because the derivative of 3y is 0 with respect to x. Okay, and this is what I'm going to get, and so I can clean this up just slightly. I'll go ahead and factor out that exponential term. So e to the x plus 2y, and then inside parentheses I'll be left with just the sine of the two trig terms. So I'll get the sine of x plus 3y plus the cosine of x plus 3y. Okay, so this right here would be our x derivative of g. Okay, cool. So now let's go ahead and compute the y derivative. So partial g, partial y. So this again, just want to use the product rule. So we'll do the derivative of the first term. So that's the derivative of the exponential, which will be the exponential itself times the derivative of x plus 2y with respect to y now. So that's just going to give us a 2. And then I'm going to multiply that with the second term, which is our sine term, sine of x plus 3y. And then I'm going to add to this the first term, which is the exponential, times the derivative of the second term. So differentiating the sine now, I'm going to get a cosine of x plus 3y. And now I'm differentiating with respect to y, so applying the chain rule, right, I'm going to pick up a factor of 3 from the 3y. All right, great. And so now I can go ahead again and just factor out that exponential term, so e to the x plus 2y, and left over is going to be 2 times the sine term. And then I'm going to get plus 3 times the cosine term. All right. And this would be our y derivative. All right, so a little bit more involved. I mean, as you know from Calc 1, right, derivatives can be a little involved. But again, the benefit here, again, is that we can just fall back on all that that previous knowledge, right, to help us in computing these new types of derivatives, these partial derivatives. All right, great. Now the last thing I want to say in this video is that there are some other notations used for these partial derivatives. So here I've just up to this point been using the del notation, del f, del x, del f, del y. So you also will see these written as the following. So for example, del f, del x, sometimes you'll see it written using a subscript, so f sub x. This is just saying take the x derivative of the function f. Okay, now sometimes you may also see this written with a capital D, D for derivative, and then there's the sub x of f. This is far less common, okay? It's these first two that are really the most commonly used notations, and then of course we would have these same notations for the y derivative. Okay, so I just wanted to point that out. We will be seeing this in the upcoming examples. All right, that is going to do it for this video.